3.2 Conservation of Linear Momentum. There are 3 learning outcomes for this subtopic that you need to cover. The first is state the principle of conservation of linear momentum. B. Apply the principle of conservation of momentum in elastic and also inelastic collision for 1D and 2D collisions. And C. Differentiate between elastic and inelastic collision. We move to the principle of conservation of linear momentum. It states that for an isolated system, the total momentum of that system is constant or conserved. Or, when the net external force on a system is 0, the total momentum of that system is constant. Mathematically, for an isolated system, total P initial is equal to total P final. P initial, Pi stand for the momentum before collision. Pf stand for the momentum after collision. Momentum is conserved for any collision and explosion. Means we can use this formula for both collision and also explosion. There are 2 types of collision. The first is elastic collision and the second is inelastic collision. These 2 collision, elastic and also inelastic collision, can occur in 1D, which is also known as head-on collision, and also can occur in 2D, two-dimensional collision, which is special name known as oblique collision. Elastic collision in one-dimensional motion, which is known as head-on collision. What is meant by one-dimensional collision? One-dimensional collision means before and after collision, it occurs along the same axis. So you can refer to this diagram. This one is a head-on collision of 2 billiard balls. Both objects, object 1 and object 2, travel along the same line, which is travel along x-axis. After collide to each other, so both objects also travel along the same axis, which is along x-axis. So this collision known as one-dimensional collision, which is only occur along the same axis. And this one is referred to elastic collision. Why this one is called as elastic collision? Because after collision, they move separately with the different final velocity. For ball 1, move with V1 and ball 2 move with V2. Since the momentum is conserved, always conserved for collision and also explosion, so you can use the principle of conservation of linear momentum, which is total P initial is equal to total P final. Or we can expand this formula, which is M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. So take note also, when you're using this equation, don't forget to consider the sign convention for the motion. So by referring to this movement of 2 billiard balls, or you can refer also to this diagram, so both objects actually travel along x-axis. So the standard sign convention, if the object's initial and final or after collision travel along x, so you can assume that the rightward motion, the value of u and v is positive. For the leftward motion, u and v is negative. If before and after collision, both objects travel along y-axis, so we can assume that for upward motion, u and v is positive, and downward motion, u and v as a negative value. Next is inelastic collision in 1D. Okay, you can refer to the collision between two billiard balls. So this one is known as perfectly or completely inelastic collision between two billiard balls. Perfectly or completely inelastic collision means after collision, they stick together and move with the same final velocity. So since the momentum is conserved, so we can use the principle of conservation of linear momentum, which is total P initial is equal to total P final. After collision, both objects share the same final velocity. Hence, the equation for inelastic collision in 1D motion is m1 u1 plus m2 u2 is equal to m1 plus m2 multiplied with v. So this collision also don't forget to consider the sign convention, which is if object initial and after travel along x, for the rightward motion, the value of u and v is positive. Leftward motion, u and v is negative value. If the object travel along y, you can consider the upward motion as a positive value and downward motion as a negative value. So this formula becomes like this for the final momentum, because finally each share after stick together, they move with the same final velocity v. So v1 is actually equal to v2, which is equal to the only v. So that's why this equation becomes like that. Okay, we move to elastic collision into D, which is known as oblique collision. Oblique collision means during the collision, it involves x and y axis. So since momentum is a vector quantity, and during this collision, for oblique collision, since it's involves x and y axis, so we need to apply the principle of conservation of linear momentum separately along x, which is total pxi is equal to total pxf. You expand this formula. Total pxi is equal to m1 u1x plus m2 u2x. Total px final is equal to m1 v1x plus m2 v2x. While for y component is total pyi is equal to total pyf. You expand the formula. The total momentum along y before collision is m1 u1y plus m2 u2y is equal to, for the total momentum along y component after collision is m1 v1y is equal plus with m2 v2y. For this 2D oblique collision, we need to put the subscript x. If you apply the principle of conservation of linear momentum along x-axis, we need to put the subscript x for a symbol in momentum p that refer to vector quantity, which is the symbol of u and also symbol of v. v1, v2, u1, u2, we need to put the subscript x. Same goes to momentum along y. So we need to put the subscript y for u and v. And the next is perfectly inelastic collision into D. For oblique collision, that also involve x and y axis. So the equation for perfectly inelastic collision for 2D, for x component is m1 u1x plus m2 u2x is equal to m1 plus m2 multiplied with vx. Perfectly inelastic collision means after collision, both objects move with the same final velocity v because they stick together after collide each other. And then for y component, when you apply the principle of conservation of linear momentum, so the equation becomes m1 u1y plus m2 u2y is equal to m1 plus m2 multiplied with vy. Vy means the component of vector v along y-axis. Vx is the component of vector v along x-axis. Next is properties of elastic and also inelastic collision. So the similarity between elastic and inelastic collision, the total momentum of the system for both collision is always conserved, which is you can apply this principle for both elastic and also inelastic collision, which is total P initial is equal to total P final. But the total kinetic energy for inelastic is not conserved, while for elastic collision is conserved. So the total kinetic energy for elastic is conserved, while the total kinetic energy for inelastic is not conserved. The value of total kinetic energy before and after you can use to prove the types of collision. If the question asks us to show whether the collision is elastic or inelastic collision, so you can calculate the total kinetic energy initial first. Next, find the total kinetic energy final. And then you compare. So if the value of total kinetic energy initial are equal to the total kinetic energy final, so we can conclude that the collision is elastic. Why elastic collision? Because for elastic collision, the total kinetic energy is conserved. Conserved means the total kinetic energy before collision value, the values of total kinetic energy before collision are equal to the values of total kinetic energy after collision. While if you compare the total kinetic energy before and after collision, if the value of total kinetic energy initial not equal to the total kinetic energy final, so we can conclude that the types of collision is inelastic collision. So based on the value of total kinetic energy before and after, actually you can determine or prove the types of collision. Okay, not to prove the types of collision based on the statement they stick together after collision or they move separately after collision, so we can conclude the types of collision is elastic. They stick together and move with the same final velocity, you can conclude it is inelastic. That is wrong, okay, because not all inelastic collision are stick together after collision. So for inelastic collision, the total energy is actually conserved. The total energy is conserved before and after when you consider the value of energy. When we consider the value of energy loss. So this energy loss is actually being transformed into other form of energy like sound, heat, or deformation. For inelastic collision, There are losses of energy, but for elastic collision, there is no loss of energy. So this losses of energy is actually that being transformed into other form of energy like sound, heat, and deformation. And the common misconception for inelastic collision that only inelastic collision the bodies stick together. This is the common misconception. Not all actually inelastic collision are stick together after collision. Only for completely and perfectly inelastic collision are stick together after collision. Perfectly or completely inelastic. Applying conservation of momentum for 1D collision. Question number 1. Figure above shows an object A of mass 200 gram collides head-on with object B of mass 100 gram. After collision, B moves at a speed of 2 meter per second to the left. So this value is represent the final velocity of ball B, which is equal to negative 2 meter per second. So determine the velocity of A after collision. So your required is to find VA. And you are given the value of UB is equal to 3 meter per second, which is directed to the right. So the value of UB is a positive value, while UA is a negative value, which is negative 6 meter per second, since ball A is travel in opposite direction to ball B, which is directed to the left. You are given the mass of ball B is 100 gram. So we need to convert to kilogram, which is 0.1 kilogram. And for ball A is 200 gram. We need to convert also into kilogram, which is 0.2 kilogram. So by applying the principle of conservation of linear momentum, which is total P initial is equal to total P final, you expand that principle, which is MAUA plus MBUB is equal to MAVA plus MBVB. Substitute the value of MA 0.2 kilogram, UA is negative 6 meter per second, MB 0.1, UB is 3 meter per second, and then MA is 0.2 kilogram, VA is our required, MB is 0.1 kilogram, VB is negative 2 meter per second, and finally you will get VA is negative 3 meter per second, which is directed to the left. So this negative value indicates that the final velocity of ball A is travel to the left. So ensure that when you're using this principle of conservation of linear momentum, whether for 1D or 2D collision, so don't forget to always consider the sign convention for U and V. Okay, which is the standard sign convention for U and V is if the motion is to the right, U and V is positive, to the left is negative, upward motion is positive, downward motion is negative. Next, applying conservation of momentum for 2D collision. So 2D collisions refer to oblique collision. So question 2, two balls A and B, each velocity is 2.5 meter per second for ball A and 1.5 meter per second for ball B, are moving in opposite direction on a table. If you assume ball A is to the right, automatically ball B is to the left. So this value should be in negative value. The balls collide with each other and bounce off. The mass of ball A and B are 2 kilogram. So 2 kilogram for A and 2.5 kilogram for ball B. So calculate the final velocity of ball B and its direction. So we need to calculate the magnitude and direction of ball B if the final velocity of ball A is 1 meter per second as shown in figure below. So by referring to this figure, so this one is an oblique collision, and when you refer to VB and VA, this vector VA and VB actually lies in between X and Y axis. So we need to resolve VA into Y and X component. Same goes to VB into X and Y component. For this oblique collision, so we need to apply the principle of conservation of linear momentum separately along X and also along Y axis. So for this case, for oblique collision, so the first step, we need to resolve the velocity into X and Y component. So you resolve VA into both components. So for Y component, you will get VA sine theta, okay, which is equal to 1 sine 35 degree, while for VAX is negative 1 cos theta. So negative value here indicates that VAX is actually directed to the left. And then next, you resolve for VB into both components, X component and also Y component. So for VBY, your VBY is a negative value because when you resolve this VBY, that vector is directed downward. Settle you resolve. Next, we apply the principle of conservation of linear momentum for both axes, X and Y axis. So for X axis, you apply that principle. So you write down that equation like that, which is total PXI is equal to total PXF. And then you expand that formula, which is MAUAX. Okay, don't forget to put the subscript X, especially for symbol U and also symbol V. Okay, plus with MB, UBX is equal to MAVAX plus MBVBX. And then substitute the value of MA, which is 2 kilogram, UAX is 2.5, MB 2.5 kilogram, UBX is negative 1.5 meter per second because ball B is directed to the left. MA is 2 kilogram. VAX is equal to negative 1 cos 35. Okay, VAX, not VA. VA is 1 meter per second. So you need to substitute here is VAX, not the value of VA. And then plus with MB VBX. MB is 2.5 kilogram. So your VBX in terms of VB and theta is VB cos theta. So you will get the first equation, which is 1.155 is equal to VB cos theta. And then you apply the same principle along y-axis. You expand that principle, so you will get MAUAY plus MBUBY. So you put the subscript y for vector u and also vector v. Okay, is equal to MAVAY plus MBVBY. The total momentum before collision along y-axis, the value is equal to 0. Y is equal to 0. So you can refer to this diagram initially. Both object, ball A and ball B, both are travels along x-axis. Hence, there is no momentum lies along y-axis. So that's why the total momentum before collision along y-axis is equal to 0. And then you substitute the value of MAVAY, MBVBY. So this negative sign is actually referred to VBY. Okay, VBY. Remember your vector B is like this. So when you resolve VBY, so you will get the direction for your VBY is downwards. So VBY should be in negative value. So you will get the second equation, which is 0.459 is equal to VB sine theta. And then step 3, equation 2 divide by equation 1. So you divide the second equation with first equation. Finally, you will get the value of theta is equal to 21.67 below negative x-axis. So this value of theta represents the direction of VB, which is 21.67 degree below negative x-axis. And the last step, substitute the value of theta into first equation or second equation, either one. And finally, you will get the magnitude of VB is 1.24 meter per second. Question 3. Figure below shows the oblique collision for two balls. Both have the same mass m. Find the velocity for both objects after collision. So this one also the example for oblique collision. So by referring to this diagram, the first object is travel towards a stationary object which is not moving. So this first object travel to the right with initial speed 10 meter per second. After that object collide with stationary object, they move separately. For object 1, travel with V1 at angle 30 degree from horizontal. While for the second ball, travel with V2 at angle 45 degree from horizontal. So find the velocity for both objects after collision. So by referring to this diagram, the vector V1 and also V2, this vector diagram actually lies in between X and Y axis. So this collision known as two-dimensional collision, special name called as oblique collision. So we need to apply the principle of conservation of linear momentum separately along X and Y axis. So before you apply, so don't forget to resolve V1 to both components. So same goes to V2, resolve to both components first. And then you apply the principle of conservation of linear momentum along x-axis. And finally, you will get the first equation, which is V1 is equal to 11.547 minus 0.8165 V2. So for this case, M is not given. The value of M, M1 and M2 is not given, but you are given in terms of M. So M1 is actually equal to M2, which is equal to M. So we can cancel out that symbol of M. So this one is equal to 0 because the second ball is stationary. So there is no momentum for the second ball because velocity of the second ball is equal to 0. And then we apply again that principle along y-axis. When you apply along y-axis, so you will get the second equation. There is no momentum along y-axis before collision because both object is not travel along y-axis. Only the first ball is travel, but it travel along x-axis. Hence, there is no momentum. There is no total momentum occur along y-axis. So that's why the value of total P y initial is equal to 0. Next step, okay, substitute second equation into first equation, and finally you will get V2 and also V1. Okay, question 4. A tennis ball of mass m1 moving with initial velocity u1 collides with a soccer ball of mass m2 that is initially at rest. After collision, the tennis ball is deflected 50 degrees from its initial direction with a velocity v1 as shown in figure below. Suppose that m1 is equal to 250 gram, m2 is 900 gram, u1 is 20 meter per second, v1 is 4 meter per second. So calculate the magnitude and direction of soccer ball after the collision. Okay, so we apply the principle of conservation of linear momentum separately along x-axis and also along y-axis. So before you apply this principle, so don't forget to resolve first that vector into x and y component. For x, for momentum along x, so you will get 0.25 times with 20 plus with 0 plus with 0 because the second ball is stationary. So is equal to 0.25 multiply with v1x, which is v1 cos theta 1, plus with m2, which is 0.9, multiply with v2x. So here for v2x, you no need to expand in terms of v2 cos theta. So just maintain in terms of v2x. If your solution is like this, so you will get the value of v first. But if you expand v2x in terms of v2 cos theta like that, you will get the value of theta first as your final answer. So you will get for v2x is equal to 4.84 meter per second for the momentum along x-axis. Next, you apply the principle along y-axis. The total momentum initial before collision is equal to 0 because no motion along y-axis. So same goes to this step, no need to expand this v to y. So you will get v to y is 0.851 meter per second. And to calculate the magnitude of soccer ball, you use the Pythagoras theorem, which is v2 is equal to v2x squared plus v2y squared. Substitute the value of v2x and v2y. Finally, you will get the magnitude of v2. Represent the magnitude of soccer ball is 4.91 meter per second. Next, we calculate the direction of soccer ball. By using the concept of trigonometry, theta 2 is equal to arctangent v2y divided by v2x. Substitute the value of v2y and v2x, and finally you will get the direction for the soccer ball is 9.97 degree. Question 5. A car with mass 1.5 times 10 power of 3 kg traveling east at speed 25 meter per second collides at an intersection with 2.5 times 10 power of 3 kg van that travel to north at speed 20 meter per second. Find the magnitude and direction of velocity of the wreckage after collision, assuming that the vehicles undergo a perfectly inelastic collision. So your required is to find the magnitude of V and also the value of theta. So we need to picture the situation by drawing a diagram first. Initially, car is traveled to east, which is actually directed to the right with speed 25 meter per second. While van is traveled to north, which is along y-axis with speed 20 meter per second. At intersection, both vehicles collide each other, and after that, it stick together and move with the same final velocity v. Our required is to find this v. And according to this diagram, the vector v is actually lies in between x and y component. When you resolve this vector v to x component, so this one is our vx. When you resolve this vector v to y component, this one is our vy. And according to this diagram, vector diagram, vector v is actually lies in between vx and vy. This vector v is actually represent the hypotenuse of vx and vy. So to get this hypotenuse v, so you can use the Pythagoras theorem, which is v is equal to the square root of vx squared plus vy squared. So to get this magnitude of v, first we need to find the value of vx first. Next, we need to find the value of vy. And finally, you will get the magnitude of v by using the Pythagoras theorem. So to get vx and vy, so we need to apply the principle of conservation of linear momentum separately along x and along y. Why we need to apply separately along x and along y? Because this collision is known as two-dimensional collision. So we need to apply separately the principle of conservation of linear momentum along x and also along y. So since the collision is perfectly inelastic collision, for x-axis, the formula is mc/ucx plus mv/uvx is equal to mc plus mv multiplied with vx. So you substitute all the values, so finally you will get Vx is equal to 9.375. The value of initial momentum for van along x-axis is equal to 0 because van is initially travel along y. There is no momentum initial along x-axis for the van. Next, we apply the principle of conservation of linear momentum along y-axis. So the equation for y-axis is mc/ucy plus mv/uvy is equal to mc plus mv multiplied with vy. For the initial momentum along y-axis for car is equal to 0 because initially car is not travel along y. The car is travel initially along x-axis. So initial momentum for car along y-axis is equal to 0. So you sum all the values, so finally you will get Vy is 12.5 meter per second. And to get the magnitude of V, remember you can use the Pythagoras theorem. Since our V is actually the hypotenuse of Vx and Vy, so use the Pythagoras theorem, which is the square root of Vx squared plus Vy squared. Substitute all the values for Vx and Vy. And finally, you will get the magnitude of V after the wreckage is 15.63 meter per second. Next, you calculate the direction of this final velocity by using trigonometry, which is Vy over tangent theta is equal to Vy over Vx. Substitute the value of Vy and Vx, and finally you will get the direction of the final velocity of both vehicles after collision is 53.13 degree above positive x-axis. Okay, next exercise. Question 1. Object A of mass 8 kg moving at 4 meter per second collides with another object B of mass 6 kg moving 5 meter per second in opposite direction. After collision, object A moves in opposite direction to its initial direction at 0.1 meter per second. A. What is the velocity of B after collision? So to get your VB after collision, first we need to list down all the information given first. Given MA is 8 kg, UA is 4 meter per second, so VA is negative 0.1 meter per second. If we let UA is a positive value, automatically VA must be in negative value because after collide with ball B, ball A is travel in opposite direction to its original direction. So VA is negative 0.1 meter per second. For ball B, mass B is 6 kg. Initial velocity of ball B is negative 5 meter per second because ball B is travel in opposite direction to ball A. So find VB. So our required is to find VB. So to get VB, you can use the principle of conservation of linear momentum. So before we apply this principle, so we need to picture the situation by drawing a diagram first. before collision and after collision. And then you expand this principle for elastic collision, which is MAUA plus MBUB is equal to MAVA plus MBVB. Substitute all the values, including its sign convention, which is for UB and VA should be in negative value. And finally, you will get VB is equal to 0.467 meter per second, which is directed to the right. Next, show that the collision is inelastic. So to show the collision is inelastic, so we need to calculate total kinetic energy initial first. Next, you find the total kinetic energy final. And then you compare these two values. If these two values not the same, confirm the types of collision is inelastic collision. So we calculate the total kinetic energy initial first by using half ma UA square plus half mb UB square. Substitute all the values and finally you will get the total kinetic energy initial is 139 joule. And then next we calculate the total kinetic energy final using the formula half ma VA square plus half mb VB square. Substitute all the values and finally you will get the total kinetic energy final is 0.694 joule. Next, we compare these two values. Since these two values are not the same, hence the collision is inelastic collision. The next exercise. An object A of mass 1 kg moving at speed 5 meter per second to the right collides with object B of mass 2 kg initially moving at speed 4 meter per second to the left. The collision is completely inelastic collision. Completely inelastic collision means after collision they stick together and move with the same final velocity V. After collision, so you need to calculate the velocity for each object. So we need to find this V. So to solve this problem, so first we need to picture the situation by drawing a diagram like this. And then take out all the information given, which is UA is 5 meter per second. UB is negative 4 meter per second because ball B is travel in opposite direction to ball A. Given also MA is 1 kilogram, MB is 2 kilogram. To get this final velocity for both objects, we use the principle of conservation of linear momentum, which is total P initial is equal to total P final. For completely inelastic collision, so the equation is MAUA plus MBUB is equal to bracket MA plus MB multiplied with V. So substitute all the values, including its sign convention, especially for UB. And finally, you will get the velocity for each object is equal to negative 1 meter per second, which is directed to the left. Next, calculate the amount of kinetic energy loss. So to find the kinetic energy loss, first we need to calculate the total kinetic energy initial using this formula, which is half ma UA square plus half mb UB square. So substitute all the values, so you will get 28.5 joule. Next, we calculate the total kinetic energy final for this completely inelastic collision. The total kinetic energy final's formula is half MA plus MB multiplied with V square. You substitute all the values. Finally, you will get the total kinetic energy final is 1.5 joule. So, to calculate the amount of kinetic energy loss is total kinetic energy final minus with total kinetic energy initial, which is 1.5 minus with 28.5. And finally, you will get the amount of kinetic energy loss during this collision is 27 joule.